You have a test coming up on my math lab at the end of the chapter test for chapter 5 this weekend. And then we have a huge exam this week or next week on Tuesday, covering pretty much half of the course. And so we're going to be reviewing the rest of this week. We'll take the test next week over Zoom. Then we'll review a couple of days for the final, and then you have that final May 24th. Monday, May 24th, cumulative final over Zoom. So I have a question before us, and it says, let's estimate the integral, the definite integral from 0 to 40, f of t dt using the left Riemann sum with 4 subdivisions. Some values of the function of f are given in the table. And so they give us t equals 0, 10, 20, 30, and 40. And then underneath, they tell us f of t is 5.3, 5.1, 4.6, 3.7, and 2.3. Those are all underneath the values of t. And then we have, if the function f is known to be decreasing, could the integral be larger than your estimate? Explain why or why not. So if you're watching the video, pause it, see if you can do that, and then turn back on the video to see if you got it right. And those in class, I'm just going to pause it, give you a few minutes to see if you can do this, and then we'll talk about it and go over it. Okay, so let's look at how to do this. So we're estimating this with Riemann sums. It tells us that we're using the left Riemann sum, and we're using 4 subdivisions. And so we have a table here and 4 subdivisions. So if we look at this as our left, that would be 0 when t is 0, when t is 10, when t is 20, and when t is 30. And so the length, notice that delta t, that length in here between each is 10. Okay. And then we needed to find the height for each piece. So we're looking at the height. And for the height, because we're looking at the left-hand side, we're going to look at the value of t on the left. So f of 0 is 1. F of 10 is going to give us the height of the second rectangle. F of 20 is the height of the third rectangle, and f of 30 is going to be the height of the last rectangle. So we want to sum this up. We're estimating. And so we have 10, the height, we can factor that out. Sorry, not the height, the width. So we know these are rectangles, so it's width times height, width times height. So f of 0, we've gotten that that is at 5.3 plus f of 10, which that is 5.1, plus f of 20 is 4.6, plus f of 30 is 3.7. And so if we sum all of these up inside the bracket, 5.3 plus 5.1, oops. Plus 4.6 plus 3.7. That gives us 100, or no, it gives us 18.7. But if we multiply that by 10, this is approximately 180.7. Okay, so we found the area or approximate area under that with left endpoints. It tells me that if the function f is known to be decreasing, could the integral be larger than your estimate? And we want to explain why or why not. Let's think about this. This is strictly decreasing. So let's just think about a decreasing function in here. So starting to decrease, that has a little bit of increase. Who knows, but it's still decreasing. And we want to look at left-hand endpoints. Sorry, trying to give myself some more room. And so if we're looking at left-hand endpoints, notice the left-hand endpoint is always going to be the largest value that our y value hits in this line segment. And so technically, my height is going to be an overestimate because this is strictly decreasing. And we talked about, there was this theorem that says that we can look at this is the upper bound of our area of that integral, or the lower bound, and the sum, or that area, is going to be sandwiched in between. And so our upper bound right here is our left-hand endpoint. This left-hand sum is going to be less than or equal to the exact sum. I'm sorry, our left-hand sum is bigger. Our right-hand sum, that's going to be the smaller one in this case because it's decreasing. So right-hand sum is less than or equal to that. And our left-hand sum is the biggest value. And so when it asked us if f of x is known to be decreasing, could the integral be larger than your estimate? Explain why or why not. Yes, because of the decreasing, the left-hand sum, the point of the triangle is going to be the highest point on the interval and could give us an overestimate. Okay, so that was that problem. And I don't know why I did this, but when I multiplied 10 times 18.7, I put 80.7. This should be 87 in here, or 87.0. So we're looking at right now a jeopardy, a review of jeopardy. And so team one has chosen summations and application for 200 points. Okay, the summation formula for I squared. Well, okay. I guess this is kind of like a review, and it would be helpful if we knew what the summation of I squared is for when we're looking at the area under rectangles. So I'm going to pause the recording, see if you guys have it, and then we'll talk about it. But that's more of just a kind of a memorization. Okay, so we have team three steals it. And what is the numerator is n, all times the quantity n plus 1 times the quantity 2n plus 1. And then that is all over 6. The next example is this is pretty average for 500 points. And that says find the average value of f of x equals 3x squared minus 2x on that interval from 1 to 4. So if you're watching this at home, pause the video and work on it and then come back. Okay, so we had an answer come up, actually a couple of them, of 16. So we're just gonna reveal the answer really quickly. And what is 16 is correct. And so there were two people that got that. Let's just give them both. I don't know if we can actually give them both the points. And let's try. Team 3 was first. Team 1 was second. Aha, we were able to do that. And then, since you were first, Team 3, go ahead and choose another category, endpoints. So trig for 500. You're shooting for the big guns. Okay, so integrate the following. X plus 2 secant x tan x dx. Okay, so the correct answer, and we got a couple people that got the same answer, was x squared all over 2. Think about what trig function that you take the derivative of that gives you secant tan x, and that was secant x. So this is antiderivative of that is 2 secant x. And then since this was an indefinite integral, we had to put that plus c. Okay, so I'll just give you guys both the points. And then going back. Okay, so Priya, why don't you go ahead and tell me what the next one you would want and how many points. Okay, so I wanted to go over those couple of questions that you guys had done. So find the average value of y equals 3x squared minus 2x over that interval 1, 4. So there's a formula for average value, and the average value is equal to 1 over the upper bound of our interval b minus the lower bound of our interval of the integral from a to b of what that function is, we're taking the average value of. And so you can see that I just plugged that into my equation for that. And then I get 1/3. We integrate antiderivative of 3x squared is 3x cubed over 3. Those 3's will cancel. Antiderivative of 2x is 2x squared over 2, and those 2's cancel. This is a definite integral, so we don't put the plus c, and we're evaluating this from 1 to 4. And so we put in our upper bound first, and if we cube 4, we get 64. And if we square 4, we get 16. So we get 64 minus 16 minus, and now plug in the lower bound. So we get 1 cubed is 1 minus 1 squared, which is 1. And so this here is 0. And we get 64 minus 16 is 48. So we have 1/3 times 48, which gives us back 16. And then the other one, again, it's just knowing what your derivatives of your trig functions are and thinking backwards. So the antiderivative of x, adding 1 to the exponent, we get 2, divide by our new exponent of 2 plus 2. And what we can take the derivative of to get secant x tan x is secant x. And then plus c. Okay, so now we're going back and seeing what you guys want for the next category and how many points. Okay, so we have let's get tricky with it for 400 points. And so integrate tangent squared y plus 1 dy. Okay, so we got the right answer, tangent y plus c, but we're going to go over how to do this. And so first thing I was thinking of, what tangent or what trig function would give me the derivative of tangent squared y? And there actually isn't one, but this right here is one of our trigonometric identities. Let me just think about it really quick. And so this is the one that is tangent squared y plus 1 is equal to secant squared y. Hold on, let me just think about that for a second. So I always tend to do it this way because I don't tend to memorize those. I only know this one. Cosine squared x plus sine squared x is equal to 1. I know that I want to get a tangent here. And so that's sine over cosine, right? So this is there it is. So if I divided everything through by cosine squared x, sorry, I just had to prove it to myself. This is 1 plus tangent squared x equals secant squared x. And so now we're taking the antiderivative or the definite integral of secant squared x. Actually, it's all y in our case, dy. And then what trig function gives us back secant squared y when we take the derivative of it is the tangent squared y. Indefinite interval, so we have to put that plus c. And it shouldn't be squared. It's the derivative of tangent gives me secant squared, not the derivative of tangent squared. So that should be like that. So we're going to definitely fund for 500 points, use the fundamental theorem of calculus to evaluate x times x squared minus 6dx on the interval from -2 to 1. Okay, so the answer should have been, I don't think you're seeing the right screen, 21/4. And so how to do that? So we're looking at that integral from -2 to 1 of x times x squared minus 6. So the easiest thing is to first do your distribution before we find the antiderivative. And so distributing the x in that integral, we get x cubed minus 6x dx. And so now we're going to take the antiderivative of x cubed, which is x to the 4th all over 4, minus, and then the antiderivative of -6x is minus 6x squared over 2. And we're evaluating this from 1 to -2. So we can simplify a little bit that second term, right? 2 goes into 6 3 times. And now we're going to go in and we're going to do our substitution. And so we're going to plug in 1 wherever we see an x in here. And if we plug in 1, 1 to the 4th is 1 all over 4 is 1/4, minus 1 squared is 1 times the 3 in front. So that's -3. Then minus what we plug in our second bound. So if we plug in -2 to x to the 4th, so -2 multiplied out 4 times is 16 all over 4. Minus, and if we plug in -2 where we see an x here, well, -2 quantity squared is 4 times that 3 gives us the 12 here. We're going to have to distribute this negative. So bringing down the 1/4 minus the 3, and then 16 divided by 4, and we distribute the negative, that's a -4, and then a negative of -12 is +12. So if we combined all the integers, we have 12 minus 4 is 8, 8 minus 3 is 5, and we have a +5 plus a 1/4 gives us 5 1/4. Or how they had it is the same thing as 20 1/4 in an improper fraction form. So we're going to try summations and applications for 500 points. A ball is thrown vertically upward from a height of 6 feet with an initial velocity of 64 feet per second. How high will the ball go if the acceleration due to gravity is negative 32 feet squared? Okay, so this is, I'm just showing you where I came to get this information. And this is just a place that you could come and you could start practicing or play some Jeopardy with some friends that know calculus. So just come into jeopardylabs.com and then you can actually create your own Jeopardy game, which could be kind of cool, or you can find your own. And that's where I just go in here and I type what I want. So notice in here, I already have some things: limits and continuity, calculus review, voting methods, etc. So if I come in here and I had just done integration review for calculus, and that pulls up lots and lots of different ones. And the cool thing is that you can highlight over the piece and you can kind of see what's going to be in that game without clicking on it and having to review it. So maybe I can blow up the screen a little bit so we can see it a little better. And so I can kind of see that, oh, this is a multiple choice. So maybe I don't want multiple choice, or some of it is. And so looking at this, to me, that was all integration. But these, let's see. This was the one that we had just pulled. So it's just a way that you can go in and you can review if you wanted to. And so I could just start the game and do this. If I wanted to, going back a little bit, notice that it says I can edit this if I wanted to and make it my own. I can print it out. So you could go to print and you'll have all the questions and the answers in there with it. Or with this, I can just say I want the questions. And then I can print it with the responses. Okay, so we moved away from the Jeopardy game, and now we're looking at write the integral, which gives the area of the region between 0 and 2 above the x-axis and below the curve y equals 9 minus x squared. Evaluate your integral exactly to find the area. So this one shouldn't be too bad. This one, it tells us we want to write our integral. It's a definite integral. Definite integrals will find area underneath the curve and the x-axis if it's above the x-axis. We're looking at the bounds from 0 to 2 of 9 minus x squared dx. Okay, and so now we want to evaluate the integral. I can tell that this is a semicircle, or actually it's a parabola facing down, shifted up 9 units, and from 0 to 2, that's above the x-axis. And so let's take the antiderivative of 9, we get 9x, minus the antiderivative of x squared, we get x cubed over 3. We're evaluating this from 0 to 2. So plugging in 2 wherever we see an x, we get 9 times 2, which is 18, minus 2 cubed is 8 all over 3, minus, now plug in 0 wherever you see an x, and that just gives us back 0. So getting a common denominator, which is 3. 3 times 18, that gives me 54 thirds minus 8 thirds. 54 minus 8, that gives me 46 thirds. And 3 goes into 46. 15 times. And a 1/3. Okay, so the next problem I have so write an integral which is the area bounded between 1 and 3 above the x-axis and below the curve y equals x minus x squared, and evaluate the integral to find the area. So again, this one, I'm just going to set this one up because it's pretty general and almost the same. But the region bounded is 1 and 3. So we're looking at the definite integral from 1 to 3. Our curve is x minus 1 over x squared. So let's rewrite the 1 over x squared as x to the negative 2 power, and that will help us take the antiderivative. Only thing that we're worried about is that is this above the x-axis the whole time? So if I plug in 1 here, and I just did it with some reasoning, if I plug in 1 here for x, I get 1 minus 1, which is 0. Okay, so that touches the x-axis, that's okay. It's not below. And if I plug any number between 1 and 3, I believe that that's a positive number, but let's just make sure. So let's find out if this ever equals 0. So it's x minus 1 over x squared ever equal to 0. See if it crosses the x-axis in between there. And I can clear my fractions by multiplying everything through by x squared. And so if I do that, I get x cubed minus 1 equals 0. I notice that this is a cubic. A cubic is factorable. And what do I get? I get x minus 1 times x squared plus x plus 1. And so x minus 1 is equal to 0 when x equals 1. 1 is this value here. In this piece, I know when a cubic is that second piece, that trinomial, when I factor a cubic, I believe it's not going to be factorable over the reals, at least. If I look at my b squared minus 4ac, I believe this is a imaginary number, which it is. And so I know that this has no real solutions. And so x equals 1 is the only piece. And I can see that this is above the x-axis from 1 to 3. So we're okay with that piece. And now it's easy to go through and take the antiderivative and evaluate that from 1 to 3. So I'm going to jump to the next one and not finish that. And so this also is another problem that we had just covered or done one similar to with that jeopardy review. So we decided, since you had one like this in the jeopardy to review, to go over a different type of problem. And so here's another type of problem. Use calculus to find the x and y coordinates of any local maxima, local minima, and inflection points of the function f of x equals x times e to the negative x on the interval 0 is less than or equal to x is less than or equal to infinity. And the y coordinates may be written in terms of e or as for place decimal. Okay, so we're given our function f of x is equal to x e to the negative x. And to find local max, local mins, we want to look at our derivative and find our critical points. And so if we look at the derivative of this, we need to use the product rule. And the product rule says the derivative of the first, so the derivative of x is 1, times the second, e to the negative x, plus the first x, times the derivative of the second, e to the negative x. So the derivative of e to the negative x is itself times the derivative of the exponent. So I usually put the derivative of the exponent first. So derivative of negative x is -1 times the original e function, e to the negative x. Once we've done this, we want to find our critical values. So our critical values are where this is undefined and where this is equal to 0. And so looking at when this is equal to 0, I have e to the negative x minus, pull that negative out, x e to the negative x. And we want to know when this is equal to 0. I notice that we can factor out an e to the negative x from both of those terms, which would give us 1 minus x e to the 0. I'm looking at when is e to the negative x equals 0, and I'm looking at when is 1 minus x equal to 0. But e to the negative x never equals 0. And if we look at taking the natural log of both sides, so we can get rid of the e, we would have natural log of 0, which is undefined. So this is never equal to 0. And then here, 1 minus x is equal to 0 and x is 1. Okay, so we have to look at the following. Is 1 going to be a max or is it going to be a min? And so a couple things that we can do. We can test our derivative on the left and the right of that to see if it's decreasing and then increasing. Coming from 0 and then we're going to infinity. So if we plug into our derivative, which was e to the negative x minus x e to the negative x, we want to see if we plug in a number between 0 and 1, so how about 0.5? Is this going to be positive or negative? So if I take my e value and I raise it to the negative, sorry, not negative, if I raise it to positive 0.5 minus 0.5 times e to the negative 0.5. Oops, that's why I wanted the minus in there. So negative 0.5 power. We get that this is approximately 0.3. So this is greater than 0. So this is increasing here. And then if we choose a value that's bigger than 0.5, so how about, and sorry, not bigger than 0.5, bigger than 1. So how about 2? So if we plug in 2 there, we get e to the negative 2 power minus 2 times e to the negative 2 power. And we get that this is less than 0. So it's decreasing. Okay, so I can see that I have a absolute, not an absolute, I have a local min. When x equals 1. I can find what that local min is by evaluating f of 1. And it told me I can leave it as e. So this would be e to the negative 1 minus e to the negative 1. Plug in 1. Oh, actually, sorry, I need to plug that into my original function. So that's going to give me 1 e to the negative 1, or 1 over e. So local min is when x equals 1 and is 1 over e. We can see if x equals 0 is a local, well, we can tell that. And why did I say it was a min when I knew it was a max? Just because I needed to be wrong. Max. So increasing, decreasing, this is a max. So I can tell that at 0, I actually have a local min. So we also have a local min at x equals 0. And if we plug in 0, it is 0. Okay, so we're already out of time, so I don't have time to go through right now to find the inflection points of that function. But remember, to find inflection points, you're going to find the second derivative, and then you're going to have to find your critical values, what set your second derivative equal to 0 or make your function second derivative undefined. And then you're going to have to test into your second derivative if it's greater than 0. So just recall, if you plug in some value, let's say that f double prime of c equals 0, and you plugged in some value, I'm going to say c to the left, cl, and it was greater than 0, this is concave up. And it has this shape. And if it was less than 0, it was concave down. And I had this shape. Okay. So we'll stop there and we'll review more tomorrow. Since we kind of really went over chapter 5 today, we'll go over graphing, graphing functions, which was pretty much chapter 4. Local max, local mins, absolute max, absolute mins, and some other things in there, L'Hopital's, optimization problems. And then the little bit of chapter 3 that we didn't get on the first exam. So we'll cover that tomorrow. Let me stop here.